A gas pipeline consists of two single pipes with a couple of parallel pipes in the middle. The inlet flow rate is 120 million standard cubic feet per day. The first pipe segment AB is 10 miles long and consists of nominal pipe size of 16 inches, 0.250 wall thickness pipe. The long BCE is 20 miles long and consists of nominal pipe size of 14 inches, 0.250-inch wall thickness pipe. The loop BDE is 15 miles long and consists of nominal pipe size of 12 inches, 0.250-inch wall thickness pipe. The last segment EF is 18 miles long, nominal pipe size of 16 inches, 0.250-inch wall thickness pipe. Assume a gas gravity of 0.6. Calculate the outlet pressure at F and the pressure at the beginning and the end of the pipe loops and the flow rate through them. The inlet pressure at A is equal to 100 psig. The gas flow temperature is 60 degrees Fahrenheit, base temperature is 60 degrees Fahrenheit, and base pressure is 14.73 psia. The compressibility factor Z is equal to 0.90. Use the American Gas Association fully turbulence equation throughout these calculations. So what we're doing is how to calculate the outlet pressure in a parallel piping system. So let's begin. Now we first write down the given information. Now we'll write down the given information. The given information, we have the flow rate, which is 120 times 10 raised to power 6 standard cubic feet per day. We also have the gas gravity to be 0.6. Now we have the temperature of the fluid, which is the gas temperature, to be 60 degrees Fahrenheit, which is equivalent to 520 degree Rankine. So that means it's 60 Fahrenheit plus 460, which will give you what? 520 degree Fahrenheit. Now, we also know that the base temperature is 60 degree Fahrenheit, which is equivalent to 520 degree Rankine. The base pressure is 14.73 psia. Then the pressure P1 at the pressure at A, at capital A, is 1000 pxig. Now converting this gauge pressure to absolute, we add this to it. So you have PA to be 1014.73 psia. Now Now we also the compressibility factor to be 0.90. Now let's now draw the flow, the equation, the, the diagram. Now from here to here, you move a distance like this is a loop now. And it joins here again and goes like this. Now you have here to be A, B. Now let's say there is a point here. You have here to be C, D. Here now is E, the point where they meet, and the last here is F. Now this segment AB is 10 miles and the nominal pipe size is 16 inches. 16 inches. And it has a thickness of 0.250 inches. Now this one, which is BCE, is 20 miles. And has a nominal pipe size of 14 inches. Pipe thickness of 0.250 inches. Now, the one of BDE is 15 miles. And a nominal pipe size of 12 inches. And thickness, wall thickness of 0.250 inches. Now let's go back. This other one has 18, is 15, is 20. Okay. It's 18 miles. And the nominal pipe size of 16 inches. And you have 0.250 inches. Now this is the way it flows. So now we have Q here. Now here and here you have what you call Q1 and Q2. So now if you look, we have been able to pull down all we needed to solve this particular problem. Now another website. So now the internal diameter of the pipe, let's say at AB will be the nominal pipe size, which is 16, minus 2 times the thickness, which is 0.25. So this 2 times this is 16, 0.5 minus this, you have 15.5 inches. Now the internal diameter of BCE loop BCE will now be equal to 14 nominal pipe size minus 2 times 0.25. So this will give me 13.5 inches. Now for this other side, the diameter, I can call it BDE will now be the normal pipe size minus 2 times 0.525. So this will give me 11.5 inches. Now, the EDEF is the same thing as DAB, which is what? 15.5 inches. So let me just say DAB is equal to DEF equal to D1, then DBCE equal to D2 equal to 13.5 inches, and BDE is equal to D3, which is equal to what? 11.5 inches. Now, we'll further reduce this now. First, we're asked to calculate what? We're asked to calculate the outlet pressure we're asked to calculate Q1, Q2, the outlet pressure at F, which is unknown, the pressure between at the beginning and the end of the loop. So this is the beginning and this is at the end of the loop. So we're asked to get P, B, or let's say P at B unknown, P at E unknown. Now, what we are going to do now is we're going to calculate first. First, for us to be able to calculate the pressure at F, through from A, we actually need to consider this loop here. There's a loop here. So for us to consider the loop, first we need to calculate. There are so many variables now. For us to solve these pressures, we need first to get the flow rate. So if we get the flow rate, we can now begin to proceed. The flow rate at each of the loops. Now, how to do that? So what we're going to do is we now make use of the general flow equation, which states that Q is equal to 38.77 F times bracket open base temperature divided by base pressure times bracket open P1 square minus P2 square divided by T gas gravity divided by the gas flow rate, gas temperature, sorry, divided by the length of the segment divided by the compressibility, all raised to power 0.5 times d raised to power 2.5. Now, if we look at this equation critically, now this is transmission factor. So this transmission factor, with respect to dimensional properties of the pipe, the gas property remains constant. So now the gas properties are like the transmission factor. This is the gas property, which is the base temperature, the base pressure, not actually is a constant at that region. So we assume it's the same all through the pipe segments. Now you have the gas gravity, you have the gas temperature, you have the compressibility factors. These are constants. Now let's treat them as constants, all of them. Now, except this, the length of the segment, the length of the segment, the diameter of internal diameter of the pipe. Now, the pressure at each point varies too. So these are all variables. These are variables now. Now, let's treat these other ones as constant. So that means the flow rate will just be the same as saying C times bracket open P1 square minus P2 square divided by L all raised to power 0.5 times D raised to power 2.5. So it invariably, this C now will be the constant. Now, but before I proceed with this, now, before we proceed with this, now, what I will do, in essence, before we proceed with this, I need to define these parameters. Although I define it very verbally, now we can say where Q is a gas flow rate, that is a volumetric flow rate, which is in standard cubic feet per day. Now you have the F, which is what? The transmission factor. This is what? Dimensionless. This is dimensionless. So we have the base temperature, which is in Rankine, degree Rankine, sorry. You have the base pressure, which is in PSI A absolute, which is in absolute pressure. Now we have the P1, which is called the upstream pressure, or you call it the inlet pressure, or you can call it okay, these are the two things you can call it. So now it's in PSI A2, then P2 is the downstream pressure, or the outlet pressure, or you call the delivery pressure if it is at the last. So this is in PXIA. Then we have the G, the capital G, which is the gas gravity. This is dimensionless. Now we have a TF, which is the gas temperature, or you call the fluid temperature. Is why they put F here. Is in Rankine, degree Rankine. You have the Z, which is the compressibility factor. This is dimensionless. You have now the L, which is the length of the pipe segments. This is in miles. Now we have the D, which is internal diameter of the pipe. This is in inches. Since F, which is the transmission factor, is not constant in this case, is not constant throughout the pipe throughout the pipeline. It varies based on diameter of the pipe. Now let's say we should use fully turbulent turbulence equation. So for fully turbulence equation, F is equal to 4 log 3.7 B divided by E base 10. Now, since F varies with respect to D, the flow formula will now be Q equal to F times C, which is a constant, bracket open P1 square minus P2 square divided by L raised to power 0.5 times internal diameter raised to power 2.5. So if you square all through, you have Q square is equal to F square C square times P1 square minus P2 square divided by L times D raised to power 5. Now, if we square both sides of the equation, you have Q square equal to F square times C square, brackets open, P1 square minus P2 square all over L. Now, raised to power 0.5 times 2, so 0.5 times 2 will give you 1 here. Now, times D raised to power 2.5 times 2, so it will give you 5. So that is why how we got this. So now, let's rearrange this equation. Rearranging this equation, removing the expression on the left, moving the expression on the right hand side to the left hand side, and that on the left hand side to the right hand side, we have C squared dot F squared dot, that is times P1 square minus P2 squared divided by L times dot, as in, which is times D raised to power 5 equal to what? Q square. So if we multiply both sides by this term, which is, if we multiply by both sides by L divided by C square F square D raised to power 5. Now, if we multiply both sides by this term, you have C squared dot F squared dot P1 square minus P2 square all over L dot D raised to power 5 multiplied by L over, bracket open, L over C square dot F divided by dot F square divided by D raised to power 5 is equal to Q square L times 1 all over C square divided by F square D square. Now, this we cancel out this we cancel out this. D raised to power 5 we cancel out, D raised to power 5, L we cancel out L. So we have P1 square minus P2 square equals to Q square L. Now, assuming 1 all over C square is equal to K, you now have K here divided by F square D square. Now, let's now make a free sketch of the pipeline system that we are analyzing. Now, here is D and L, here is D1, here is D2, so, and this is L2, L1. So, and here is F1, here is F2. So, now we have here to be B, here is A is C, here is D, here is E, and here is F. Now, this D is the same, but here will be L3. So the diameter here, internal diameter is equal to the diameter at the end. So now, we also note that now, according to the law of continuity, at any node on a pipeline, a gas pipeline, or any fluid, the flow rate coming into that node is equal to the flow rate leaving the node. So now we have here to be our Q. Here is Q1, here is Q2. So we have Q to be equal to Q1 plus Q2. This is equation 1. Now, according to also according to the law of parallel flow, for a parallel flow at each two nodes, the potential difference between two nodes are the same, no matter the route you take. Now, we took this loop BCE and BDE. So, the potential difference or the pressure difference, not the pressure difference between BE is the same no matter the route you take. So, that means the pressure at B square minus the pressure at E square is equal to K with a constant Q1 square L1 divided by F1 square divided by D1 square is equal to KQ2 square times L2 divided by F2 square times D, not D square, is D raised to the power 5, D raised to the power 5, D2 raised to the power 5. So now let's work with this equation. We have K Q square Q1 square L1 square all over F1 square D1 raised to the power 5 is equal to K Q2 square L2 divided by F2 square times D2 raised to the power 5. So this will cancel out this here. Now from this equation it means that Q1 square divided by Q2 square is equal to D1 all over D2 all raised to the power 5 times F1 all over F2 all raised to the power 2 times L2 all over L1. Now it means that Q1 all over Q2 is equal to, now this, note that this expression Q1 square all over Q2 square is same thing as Q1 all over Q2 all raised to the power 2. So it now implies that Q1 all over Q2 will now be the square root. If you do the square root of both sides. So the square root of both sides, you have D1 all over D2 all raised to the power 5 times F1 all over F2 all raised to the power 2 times L2 all over L1. This will give us F1 all over F2 times the square roots of D1 all over D2 all raised to the power 5 times L2 all over L1. Now, let's go there now. Now, let's calculate F1. F1, we're using the formula. You have log bracket open 3.7 D divided by E base 10. Now let's assume E is equal to 700 micro inch. So we now have 4 log 3.7 times the D1. D1 will now is 13.5 divided by 700 times 10 raised to power minus 6 is 10. So this will give us what? So this will give us 1 times log 3.7 times 13.5 divided by 700 times 10 raised to power minus 6 times log 3.7 times 13.5 divided by 700 times 10 raised to power minus 6 bracket close equal to, so we have 19.41. So F1. Now F2 will be 4 log bracket 3.7 times D2 all over E base 10 to 4 times log 3.7 times 11.5 divided by 700 times 10 raised to minus 6 base 10. So we have 4 times log 3.7 times 11.5 divided by 700 is raised to power times 10 raised to power minus 6 equal to 19. This is 19.13. Now F, which is the one on the main pipeline, which is 4 log 3.7 times D divided by E base 10. So we'll say 4 log 3.7 times 15.5 divided by 700 times 10 raised minus 6 base 10. So we now have 4 times log 3.7 times 15.5 divided by 700 times 10 raised to minus 6 bracket close equal to, this is 19.65. So it's approximately close. So now let's look at Q1 all over Q2, which will give us what? That is F1 all over F2 square root of D1 all over D2 all raised to power 5 times L2 all over L1 raised to power, okay, raised to power nothing. So we have now F1, which is 19.41 divided by 19.13 times the square root of B1, which is 13.5 divided by 11.5 all raised to power 5 times L2, which is 15 divided by 20. So this will give us what? Now let's work it out. Let's now make use of our calculator. We have 19.41 divided by 19.1. This should be 14, sorry, 14. We have 19.14 times the square root, bracket open, 13.5 divided by 11.5, bracket close, raised to power 5 times bracket close, bracket open, 15 divided by 20, bracket close, equals to this is equal to 1.311306017. Now implies that Q1 will now be equal to 1.311306017Q2. Now, since we have gotten this should be our equation. What this? This is equation 1, this is equation 2. So from equation 2, we got this. We'll add this, which is equation 4. Let me go back. Equation 3. Now this should be equation 4. Now from equation 1, we have Q is equal to Q1 plus Q2. Now since we have gotten Q1 to be equal to in terms of Q2, so we substitute it into this equation 1, we have Q is equal to 1.311306017 Q2 plus Q2. This will give us 2.311306017 Q2. So Q2 is equal to Q all over 2.311306017. So, and Q is equal to 120 times 10 raised to power 6 divided by 2.311306017. So let's now work it out. We say 120 times 10 raised to power 6 divided by 2.311306017 equal to, so this will give us what? It means this is 51.91698397088,975. So I could say approximately Q2 is times 10 raised to power 6. So approximately Q2 is 51.92 times 10 raised to power 6 standard cubic feet per day. Now Q1, which is the same thing as Q minus Q2 from equation 1. Let me just write it from equation 1. We now have 120 times 10 raised to power 6 minus 51.992 times 10 raised to power 6. So minus, this will give us 120 times 10 raised to power 6 minus 51.92. So you have 68.08 times 10 raised to power 6 standard cubic feet per day. So we have Q1 to be 68.08 times 10 raised to power 6 standard cubic feet per day. We have Q2 to be 51.92 times 10 raised to power 6 standard cubic feet per day. So we have gotten the flow rate. Now the next thing is to calculate the pressure at the beginning. Now let's make a little sketch. We have this sketch to be like this. We have A, B, C, D, E, F. Now we are asked to find this, and this, the pressure at those points. Now let's start with this. We know that F, the transmission factor at this segment, is 19.65. So that is what we got here, 19.65. So we're going to make use of the compressibility, the compressibility factor is constant. So now we're going to make use of the general flow equation. Where the flow rate is equal to 38.77 F times base temperature all over base pressure times bracket open P1 square minus P2 square divided by G, there's gas gravity times the gas temperature times compressibility factor times the length, bracket close, all raised to power 5 times D raised to power 2.5 times D raised to power 2.5. So now you have the first one, the first segment, points A and B. So and we know the flow rate here, which is Q. We know Q1, we know Q2. We know this one also, this is Q. Oh, for this segment, the Q there is 120 times 10 raised to power 6, which is equal to 38.77 times the transmission factor is 19.65 times the base temperature is 520 divided by 14.73, which is the base pressure, times bracket open. We know the pressure here P1, which is P at A, to be 114.73 raised to power 2 minus PB, that is what we're looking at, P pressure at B squared divided by G 0.6 times the temperature, the gas temperature is 520 times 0.9 as the compressibility factor times the length of this is 10 miles. Let me see. It's 10 miles. Let's look at the back. Let's go back. 10 miles, yes. So this is 10 miles. Bracket close, raised to power 0.5 times D here is 15.5 raised to power 2.5, because at least is the nominal pipe size is 16. So if you calculate the internal diameter is 16. So if you calculate the internal diameter is 15.5. Now let's make pressure square difference a subject of formula. Now to do that, we rearrange this. We have 10 14.73 square minus PB square all raised to power 0.5 is equal to, now it's equal to 120 times 10 raised to power 6. Now you divide it with this and this, so divide by 3, 8.77 divide by 19.65 times, you times it with 14.73 divided by 520. Now times 0.6 bracket open, 0.6 times 520 times 0.9 times 10 raised to power 0.5 divided by 15.5 raised to power 2.5. So that is that. So now let's calculate. Let's use our calculator to punch this out. So you have 120 times 10 raised to power 6 times 14.3 divided by 38.77 divided by 19.65 times bracket open 0.6 times 520 times 0.9 times 10 bracket close raised to power 0.5 divided by 15.5 raised to power 2.5 equal to, now we have now 1014.73 square minus P at B, pressure at B square, brackets, close all in brackets, then raised to power 0.5 is equal to, now is equal to 129,855,102,984. So squaring both sides of this equation, you have 1014.73 square minus P at B, pressure at B square raised to power 0.5 is equal to, now squaring both sides, you square both sides now. You have 1.1, sorry, now 1.129, you have 12985.910 2984 all squared. So now we have squared. If you squared, this one will cancel out this. You now have 1014.73 square minus P at B square is equal to what? 129,855.9102984 square. Now making P at B square the subject of formula, you have P B square is equal to, now you move this, now it becomes 1014.73 square minus 129,985 129,985.9102984 square. No, no, no. There is an error here. This is not properly calculated. Let's work it out again. It's not supposed to be bigger like this. So let's work it out again. 120 times 10 raised to power 6 divide by 38.77 divide by 19.65 times 14.73 divided by 520. Divide by 15.5 raised to power raised to power 2.5 times bracket open 0.6 times 520 times 0.9 times 10 bracket close raised to power 0.5. Yes. Yes. So this is wrong by calculation. If you calculate this, it's wrong. So let's now clean this off here. Let me also clean it up here. It's not correct here. Not correct here. It's not correct here. No, by competition, we just made a mistake. Now, so it's supposed to be 249.97 to 135 18923. So let's go to the next page. That means here should be 249.97 to 135.18923. So this is 249. This is point here. Let me see whether I put the point there. Yeah, the point is there. 0.97215.18923 square. So this should be this minus 249.972.135.18523 square. So let's work this out. Now we square this minus 14.73 square so that means PB square will be equal to what? 967 190.528 9368. So let's take the square root of both sides. Sorry, the square root of both sides. How PB square will now be the square root of both sides. PB square, this one will cancel out this, so you have to remove this. So the square root of that expression, the square root is equal to, that will be 983.458, 644,035.9 pxia. So the pressure at B will now be 983.46 pxia, which now converted to PSIG, you have your minus 14.73 from 8. You will now have, okay, sorry, this is approximately this. Pressure at B will now be approximately 968.73 pxia. So that's the pressure at B. That is at the beginning of the loop system. Now let's now go to the next one. The next one we have, let's draw the piping system again. Don't mind my drawing. You have A, B, you have E here, you have F. Now we know the flow rate here, Q1, we know the length, we know the F1, we know what again? We know the diameter D1. Now we need to calculate E here. So let's make a general expression that we're going to be using to find this. Now we have Q to be equal to 38.77 F bracket open base temperature all over base pressure times bracket open P1 square minus P2 square divided by gas gravity, gas temperature, the length of the pipe segment, and the compressibility factor, all raised to power 5, bracket close, all raised to power 5 times D raised to power 2.5. Now, with this, we can now rearrange this expression to mean that P1 square minus P2 square is equal to what? Q divided by 38.77 F times base pressure divided by base temperature. Now, then 1 all over d raised to power 2.5. All of this square. All of these square, because all of this square times q1, that is times not q1, no, times gas gravity times gas temperature times the length times compressibility factor. So that is it. So now, so if you rearrange this equation, you will have this. Now let's say we are looking for pressure at F at E. So we will now be using this expression. So what we're going to get now is now, say, we'll now roughly say P B square minus PE square will now be equal to, now here will now be Q1. You have Q1 all over 38.77 F1 times PB all over TB times 1 all over D1 raised to power 2.5 all squared times G times T, gas temperature times L, length of the pipe segment times the compressibility factor. Now the L is 1, so the compressibility factor, the gas temperature, and the they are all constant, so that doesn't change. Now let's go to the next page. So that means PB square minus PE square is equal to Q1. We know our Q1 to be what? Q1 to be 68.08 times 10 raised to power 68.08 times 10 raised to power 6 divided by 38.77 times 19.41, because F1 is 19.41 F1, F2 is 19.14. So now times base pressure is 14.73 divided by base temperature times 1 all over D1 is 13.5 raised to power 2.5 all squared times gas gravity 0.6 times gas temperature 520 times the length L1, which is here. This will be 20. L1 is 20 miles, so we use the 20 miles times compressibility factor 0.9. Now let's calculate. Then now we Let's calculate this first. So we have 68.08 times 10 raised to power 6 divided by 38.77 divided by 19.41 times 14.73 divided by 520 divided by 13.5 raised to power 2.5 equal to this. Equal to this. Now we square. So we'll calculate the whole of this. Inside these brackets, we have 3.82704168472 square times 0.6, this one, times 520 times 20 times 0.9. So we'll now have what here. So let me square this times 0.6 times 520 times 20 times 0.9. So I have 8252.329,085,794. So PB, pressure at B minus pressure at E square. So now pressure at B is 983.46 square minus pressure at E square is equal to 82,253.329,085,5,794. So this will be making pressure at E subject of formula. Pressure at E square is now equal to 983.46 square minus 82,253.329,085,5,794. So P at E square will now be equal to 983.47 square minus 82,253.3299,085,5,794 will now be equal to will be equal to 840.242.514.4206. So taking the square root of both sides, you have P at E equal to the square root of 884,940.24251444206. Now it will be equal to what? This will be 940.71 PXIA, which to PSIG it will now be minus 14.73. From it you have what? 925.98 PSIG. So we have gotten the pressure at E, gotten the pressure at E. Now the last but not the least is to get the pressure at F. We're going to make use of this formula which we derive. So pressure at E square minus pressure at F square is equal to what now? Making use of this expression is equal to Q all over 38.77 F times P base pressure all over base temperature, bracket open, base pressure all over base temperature, now times 1 all over d raised to power 2.5, bracket close square, times, now you have gas gravity times the gas temperature times the length times the compressibility factor. So the length is L3 and L3 is what? 18. Is 18. Let's go back. Let's go back to here. It's 18 miles. 18 miles. So that is what we're going to use here. Now the flow rate is the same from the beginning because the flow rate is 120. Got to converge. Now look at the drawing. Now here is A, B, C, D, E, F. So we're looking at this point now from here to here. Now they converge here. So Q1, Q2 converge to give you your Q. And here is also Q. Here Q splits to give you Q1, Q2. Here it converges to give you Q1, Q. So the value of Q here is same value here. So now that is it. Now we are looking for F here now. Okay. Now P at E square minus P at F square is equal to 120 times 10 raised to power 6 divided by 38.77 divided by 19.65 because the transmission factor is the same at this point. Here is equal to here because the diameters are the same, times 14.73 with the base pressure divided by 520 times 1 all over 15.5 raised to power 2.5 times 0.6 times 520 times 18 miles times 0.9. The whole of this square. Now let's work it out. Let me write it down again so that it will not get confusing. 120 times 10 raised to power 6 divided by 38.77 times 19.65 times 14.73 divided by 520 times 1 all over 15.5 raised to power 2.5 all square times 0.6 times 520 times 18 times 0.9. So this will be what? Let's look at it. Let me just calculate all together. So I'll just say first bracket open 120 times 10 raised to power 6 divide by 38.77 divide by 19.65 times 14.73 divided by 520 divide by 15.5 raised to power 2.5 bracket close, bracket close, raised to power square now times 0.6 times 520 times 18 times 0.9 equal to let me see, 120 times 10 raised to power 6 divided by 38.77 divided by 19.65 divided by 14.73 divided by times 14.73 divided by 520 divided by 15.5 raised to power 2.5 2.5 2.5 bracket close all square times 0.6 times 520 times 18 times 0.9. So what we have here is 114.92470.913.5. PE is 940.971. So 940.71 square minus PF square is equal to 1 112.474.923.067.9135. Now rearranging this, making pressure at F square subject of formula, you have P F square will now be 940.71 square minus 112.474.923.067.9135. So PF, now taking the square root of both sides, you have PF to be equal to the square root of what? Square root of 940.71 square minus 112.474.067.9135. Or 7.92306799135 equal to 772 equal to 77 to 463. Now the square root of this will give us what? This will give us 878.90 psi. So pressure at F is 878.90 psi. Now approximately, so which to gauge minus 14.73, we have 864.17 psig. So this is the final answer. So we have calculated the pressure the delivery pressure. So now, if you look at the diagram now, we have calculated the pressure at B, the pressure at E, and the delivery pressure, which is the pressure at F. So this is the final answer. Thank you for watching. Have a nice day. Please do well to subscribe to my channel. So when next time I make new video, you will also be the first to watch. Thank you and God bless.